close this out. I'm gonna share my screen. Okay, so of course it starts out with an article. And so I'm gonna quickly summarize the article and then we'll get into the videos. So we've been working on a table one at a time. We have seen multiple tables. There is no limit to the number of tables that you can have. And in general, this is touching on database design a little bit, but we want to, in general, have more rows than we have columns, right? So columns are going to be our table structure. We can have multiple tables. We can put data in two separate tables, and then we can use something called a foreign key in order to relate those two rows together. So most of the time we have our data distributed across multiple tables, and those tables are related to each other. Let's say that we have this table with all the students, the name, their email, the test, and their grade. Well, we run into a problem when we also store information about the books that they've read, right? Because if we look at the detailed student information, we are seeing some duplicated information, right? What happens when a student goes to change their address, right? What if Peter is no longer at peterrabbit.com? We need to update it in multiple tables, and that's not a good idea. Well, what happens if a name changes? What if Alice gets married and chooses to change their last name? Well, now we've got the same problem of, well, their name is here. If we update it in one table, but we don't update it in another table, now we may not be able to know that Alice, who has a 95 in chemistry, is no longer related to this Alice who has read the two books. What we are able to do is basically say, hey, let's take the email out of the grades table, and instead we can replace it with a student ID. And with that student ID, we are able to also do that in the book table and store everything like this. So now we are able to do what we call a join table to say, hey, the student ID and the book ID are related to each other. So go get student ID 1 from the students table, go get book ID 2 from the books table, and because those two IDs are related to each other, we're able to tell that student ID 1 is related to book ID 2. So how do we do that? How do we write a query to basically pull that relational data in so the results of the query show all the data that we want? Well, we do that with a join statement. So that's what we're going to look at right now.
I've set up two tables.
No, I can't hear you.
Detailed information. I've set up two tables in this database. A students table with detailed information about each student, like their name and email, and a student grades table, which has their student ID, test name, and grade. Let's see what happens if we just select everything from student grades. Ta-da! Okay, so we see student IDs, test names, and grades. I'd actually rather be able to see student names, emails, that sort of thing. Now, what you might notice is that the student ID in student grades is related to the ID in students. So this 1 here is actually referring to Peter Rabbit, and this 2 here is actually referring to Alice in Wonderland. Now, I want to form a query that will output the student name and email next to each test grade. And that information is in 2 different tables. So that means I need to join the tables. And there are a few ways that we can do that in SQL, and we'll try them all out actually. The simplest is called a cross join. And I can make that happen just by putting both table names after the from. Ta-ta! So as you can see, lots of rows. And basically what this did is that for each row in the first table, it created a row for each of these rows here. That means we end up with 8 rows because it creates 4 rows for each of these 2 rows. This is the simplest join, but it's also the least useful. We don't want every row matched with every other row. We only want them matched if the student ID matches. Now we can do that using an inner join, which isn't actually much more work at all and is way more useful. So there's actually a few ways of doing an inner join. We'll start with just building off the last query, and we can add a where. And the where will check to see that the student ID matches students.id. All right, so now we actually have what we wanted, is test grades next to names, because it's done the cross join and then just limited to the rows where those columns were the same. Great. This syntax here is called an implicit inner join, and it works, but it's not actually the best practice. The better way is if we do something called an explicit inner join. And that is using the join keyword. So to do that, we're going to start with just doing from one table. And actually, I'll do from students, and then join on student grades. And then instead of where, we do on. And that specifies what columns are being matched. So on students.id equals students grade dot student ID. All right, so now we have the same results as before. Switched, but really the same. Now that I have these tables joined, I'm just going to whittle down the columns I'm outputting to the names, the email, the test name, and the grade. Okay, beautiful. Now, the cool thing is, once we've done joins, we can still use where and group by and all those fancy things. Like, let's say that we want to filter down the results to just grades greater than 90. Woohoo! Let's see. Oh, no. Grade. There we go. Haha. Lots of ones above 90. Now I can email all those students with a high five. Okay, but what would happen if my tables both contain columns with the same column name but different meanings? Like right now, our student grades table has a grade column. Well, what if my students table also had a grade column for their overall class grade? That would mean down here, when we selected grade, it wouldn't know which table to pull it from because there'd be a grade column in both of our tables. So actually, to be super safe, we should prefix our columns with the table name that they're from. So we say students.firstname, students.lastname, students.email, studentgrades.test, studentgrades.grade. Okay, now we know that we're going to get the columns from the table we expect them to be in. Great. Now that is our basic explicit inner join, and it is what you'll use for most of your joins across related tables. But if you stay tuned, I'll show you a few other types of joins as well.
So this is the most common join type that we will be using. Obviously, we will cover the other types of joins, but this is the heart of relational data, which is, hey, I've got data in one table and data in another table. If I store the ID from one table, let's say the students table, into another table called grades, called student grades, I want to be able to say, hey, this student has multiple grades. That is what is called a one-to-many relationship that we'll learn about in database design on tomorrow. Well, when we have that relation, we need some way to join it together to say, hey, this student has this first name and last name. So the easiest kind of join is an inner join, whether it's explicit or implicit. It's kind of like controlled or uncontrolled inputs in React. Either one gets the job done. But the idea here is we say, hey, when we have a student ID in the students table and we store that ID over in the student grades table, we are able to use the foreign key that relate in the student grades that relates to the primary key in the students table. When we join those two together, basically say match this foreign key up with this primary key, we do that inner join, and that's what allows us to access the information in both the students table and in the grades table. Does that make sense? Go ahead and give it a try in the challenge, and then vote in the poll when you are ready to go over it. And I just put the link in the chat if you need it. Sorry, I realized I didn't share that earlier. Don't forget to vote in the poll if you were able to get it going, and then we will do a review in a minute or two. All right, let's go ahead and go over these. Okay, so they're asking us, we've created a database for people and hobbies. Each row in hobbies is related to a row in the persons via the person ID column. In the first step, insert one or more row in persons and then one or more row in hobbies that is related to the newly inserted person. So why are they asking us to do that? They want us to understand, right, the relationship here between the ID here and the person ID over here. So what we need to know is, hey, what's the next new ID that we can insert? So I'm going to say insert into persons the name and age values max, and let's pretend that I am 1. Now, if I select everyone from my persons, I should be able to see, excuse me,
Did you miss a from?
my God, I am missing words like crazy. Thank you. I can see that Max was inserted with an ID of 6. So now I need to use that ID of 6 to insert into hobbies a person ID and a name. And then I'm going to do the values. And the ID of the person is going to be 6. And then the hobby is going to be, I don't know, teaching. And that is where we are able to relate the data together. Now it says, okay, if we move on to the next step, it says select the 2 tables with a joint so you can see each person's name next to their hobby. So we are going to say select the person's name and the hobby's name, and we have to do the period here because name exists in both tables. So if we try and do a join and we just said we'll select the name, it's like the name from where? The name from persons or the name from hobbies? So in general, usually a good idea if we're doing a join to prefix the column's name with the table name that we're pulling it from. So we'll say from persons, and we will join the hobbies table, and then we got to tell it where to join, because otherwise it gives us max, 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 and everyone's hobbies, right? So when we're joining the 2 tables together, if we don't explicitly tell it where the overlap is, it's just going to mesh all the data together, and that's not what we want. So we say join on the person's ID is equal to the hobbies dot person ID. And now we can see Max is teaching and then all of these other people and their hobbies over here. So storing the data properly, good database design across 2 tables, and then being able to merge that data back together. Final step, add an additional query that shows only the name and hobbies of Bobby McBoatface using join combined with where. So we can copy that last statement we can reuse that. This time we're just going to do a where, and we're going to say where the person's name is equal to Bobby McBobby face. And that filters down our results to just the 2 that we want. Austin.
I actually got stuck on step 2 and I was trying to follow along with you. I put what you put and it's not letting me go to the next step.
Go ahead and share your screen. Chances are Joe will find it quicker than I can, but we'll give it a shot.
You're on statement.
Oh, take out your select star from persons or comment it out by clicking on that and command slashing.
Oh, okay.
I just do that as an example so I can see like what the data structure is, but then it gets really picky because it's getting a table back that isn't exactly the way they want it to look like.
Gotcha.
Okay, any questions on these 3 challenges before we move on? Okie doke. If you're joining us a little late, we already did attendance. The secret word is relational.
I'm back with my related tables about students, with the students and the student grades. And I added a new table to keep track of what projects students are working on. And once again, this one has a student ID to relate it to the students table, just like the student's grade had. And it also has a title for each project. Now what I want is a list of student names and the projects they're working on. So that means I need to join student projects with students. We can do that, as you probably guessed, using an inner join that we just learned. So what do we want? So we want students.first name. We want students.last name. We want the title of the project, so from the students projects table. And then we'll say from students, join student projects, and on students.id equals student projects.studentid. All right, so I see one project, Peter, and his very promising Caratapult experiment. But where is my other student, Alice? Well, we're missing Alice because an inner join only creates rows if there are matching records in the 2 tables. There's no row for Alice because there's no row in student projects that has Alice's student ID in it. And this makes sense, and oftentimes with joins, we do only want rows where the records matched. But in this case, we want a comprehensive list of every student and their project, and we want every student to be on that list, even if they don't have a project yet. And that is where an outer join is super useful. And it's really easy to use. We're just going to go right here and type left outer. Ta-da! Now we see Alice, and there's a big old null for the project title. Okay, so how this works is that the left tells SQL that it should make sure to retain every row from the left table, which is the one after the from, students. And the outer tells it that it should retain the rows even if there's no match in the right table, which is student projects. And that's our outer join. And there's a lot of cases where you might find you want an outer join. And just keep in mind that the behavior of inner versus outer joins. There are also some other sort of outer joins. There's a right outer join, and it basically does the opposite, is make sure that it keeps everything from the right and then joins with the left. We don't actually support right outer joins here, but if you want that, you can just switch the table order and it's the same thing. So you don't actually need to have a right outer join. You can always use left outer join. And there's also something called a full outer join, and that matches rows, if it can, on both the left and the right side, and fills in nulls when it can't on either side. And that's pretty interesting, but also is not supported in our environment here. And that is one of the interesting things about learning SQL. I'm showing you lots of things that work here and work in other SQL environments, but every environment is a little different. So you'll constantly be tweaking the tools in your SQL toolbox for each new environment. And that's true about a lot of things with computers, honestly. You'll learn the general techniques and then learn how to adapt it for a specific language or app or environment. And you basically just get really good at learning. So, yay!
So lots of different join types. There is really helpful diagrams on this. So I just pulled this one off Wikipedia. I will throw the link in the chat. But the general idea here, right, is, well, if we do an inner join, that's usually our most helpful one. That's the one at the top here. That's saying find where A and B overlap, and all we care about is the overlap of the data. But sometimes we may be looking for something like what we just learned, which is the left join, where we are the left, yeah, this is, sorry, the outer join, where we're basically saying, hey, we want the information if there is a match, right? But we also want the information even if there isn't a match. So this is the left join that we're doing here. And that is basically saying, hey, if they haven't done a project, I still want to be able to see that student's name so I know they haven't turned anything in, right? And so that's what this left outer join is really helpful at, is saying, hey, give me all of the students, even if we don't have a project that they have turned in. So if this diagram makes sense to you, great. If it doesn't, that's completely fine. There's no difference between the left join and the right join, other than obviously, do you want all the data from the left table or do you want all of the data from the right table? And then there are things called full outer joins, where you basically find information from both tables where nothing overlaps. That's a little less common. Anyway, don't worry too much about the different join types. We are going to finish going through this, so you guys have an idea of how to do multiple joins. But the most important one by far is going to be your inner join from there. Joe.
I know you told us not to worry about it, but that you explained the use case, and from the diagram, it looks like full outer join would do the same thing, at least in this use case, for trying to figure out if the data exists somewhere in the table, right? Because down bottom left.
Bottom left. Yeah, so this is the this is what we just learned how to do, which in SQLite, which is what the Khan Academy uses, this is a left outer join. This would return everything in the projects table, even if the project didn't have a student associated with it.
I see. I mean, practically, it wouldn't. You wouldn't enter a project into if a student didn't make it, right? Like in a real world example.
Not necessarily. Someone could have forgotten to put their name on the project, but you still wanted to give it a grade. So, you know, that kind of thing. So it would matter slightly. And I think what they're saying is SQLite doesn't really support a full outer join. So this is a full left join. But the left join is, or I'm sorry, the full outer join is basically the combination of this and this.
Gotcha.
Which would kind of be like selecting both tables, period. So yeah, these are, we definitely use the inner join the most. And then it is possible to see a left join or a right join. Very rarely do you see these types of joins where a key is null. But you could be coming in here and saying, well, show me all of the students who have not submitted a project. That's what this would be for. And then you could come down here and say, show me all of the students that don't have a project, or show me all of the projects that don't have a student. You know, that's basically what the join types would be for. Or show me all the data in all the tables, period. Doesn't matter if they overlap or not. Okay, go ahead and give the challenge a go. You are going to be coming up with a query that lists the name and email of every customer, followed by the item and price of the orders they've made. Use the left outer join so that a customer is listed even if they've made no orders, and don't add any order by.
Uh,
Like most of you guys are submitted. Give you guys 1 more minute and then we'll go through the answer. Terry.
Is there a real difference between left join and left outer join?
A left join by default is an inner join unless you are explicit and call it an outer join, and then it is different. So a join left outer. No, sorry, I got that wrong. Inner join is always going to be the overlap. A left join is an outer join by default. I got those two mixed up. So no, there is not a difference between a left outer join and a left join. Okay, let's go through this together. Okay, so use the left outer join so every customer is listed even if they have made no orders. So we are going to say get the customer's name, get the customer's email, get the item that they ordered from the orders table, and get the price also from the orders table. We're going to say that comes from customers, and we're going to left outer join because we want all of the customers, even if they're not in the orders table, and then we need to tell it where the overlap is. So the customer's ID matches the orders customer ID over here. And that says, okay, now the Doctor Who has ordered a sonic screwdriver and a TARDIS. We're able to see the price. That is both coming from the orders table, but then we're also able to get information on the name and the email coming from the customers table. And we are able to see that Captain Awesome here created an account, but then never made an order, right? And so that's why this use case is helpful. Okay, step 2 is another query. They still want the name, email, and total amount of money they spent on orders. Sort the rows according to the total money spent from most spent to least spent. So we're going to reuse a lot of this query. We're going to use the customer's name, still the customer's email. This time we want the price of everything added up from their orders. So we are going to say do the sum from the order's price. And they want us to call that total. So we're going to say as total. We're going to do that from still the customers table. We are going to do a left outer join on our orders table. We still are going to link the customer's ID to the customer's ID from the customers table. That will give us a giant number here. The problem with this is that this is just one customer. So what we need to do, because we did a total here, because we're doing a sum, we need to tell the database how to do that sum. So we're going to say group that sum by the customer's ID. And that does get us the answer, not completely finished though. What we did not do is sort the rows based off of the total money spent. It just so happened that we got lucky and that was the right order of things, but we should add a order by on here that does the order's price, and we would say that is descending, and that fixes the problem.
Should it actually be orders total?
Yes, we could do that as well. And we can use the alias that we created here, and that will also sort it the same way. They have to buy brooms at the broom shop in Diagon Alley. They can't they don't like make them magical themselves. Uses some kind of wood. Sorry, Joe asked in the chat, in case you don't have chat up, do they like go to Home Depot to buy broomsticks? Because there are high quality broomsticks in here. Okay, moving on. Unless anyone has questions. Okay.
I'm back.
This one is kind of a hard one to wrap your head around, but it does have practical use cases, so just warning you that in advance.
With just the table about students this time. I've added one more column to the table, buddy ID. See, I decided that every student should have a buddy, somebody that they can pair up with, do assignments with, study with, all of that. Now, the buddy ID is what it sounds like. It's an ID that relates to the ID of the student that they're buddied up with. So, for example, here, Peter is buddied up with 2, and 2 is Alice. Let me just do a select that should make that more clear. So select the ID, first name, last name, buddy ID from students. Okay. The interesting thing here is that this buddy ID is a column in a table that's related to another column in the same table. That's a bit different from before, where we'd have columns related across different tables. So, what if we wanted to show the names of each student next to the email of the buddy? Not just the ID, the email. To do that, we need to actually join the students table with itself, because the 2 bits of related data that we need both happen to be in the same table. We can do that by, let's see, so we want the first name, last name, email. So to join students with itself, we're going to write from students and then join students. Okay. All right. Okay, so we get an error. First name is an ambiguous column. And that's true. We're telling to select first name, but it's joining across 2 tables, and both of these tables have the same column names. And before, we would just prefix these with the table names, but we can't do that here because actually they're both named students. So we need to give it a way to distinguish between this one and this one, even if they're kind of the same thing. And we can do that by giving one of them an alias. So we're going to write the alias right after here. The alias is like a nickname. So here's the alias, buddies. And then we just have to specify that the email is coming from buddies.email. Haha. There we go. Now we're seeing too many rows, way too many rows, and that's because we don't have an on clause yet. So it's just joining every possible row with every other one. Now our on should check that the buddy ID from the students table, that first one, matches the ID from the second table, buddies, or what we called buddies. Haha! Now we can see Peter with Alice's email address, Alice with Peter's, etc., etc. To make this results table even a little more clear, I'm going to rename buddy's email as buddy email? Okay, so now it's a lot more clear that we're looking at Peter Rabbit and his buddy's email. Cool. Now this type of join is called a self join, and that's because it's a table being joined to itself. You can try this out in the next challenge, and I'll show you one more way to use self joins in the talk through after. I hope you'll join me. If not, just join yourself.
So think about this as you're basically making a copy of the students table so that you can join the two together, right? And so this is a very useful use case of this of, hey, I've got all of this data and all I want to do is know the person's name and their buddy's email. Well, their buddy's email is stored in buddy ID, which is self-referencing it as up here. And so what we are able to do is basically say, hey, join the table to itself, but call the copy of that table buddies. Now we have basically copied the table so that we can reference the two and join them to each other. Joe, this could be uppercase or lowercase. SQL is mostly case insensitive, but because as is a reserved word, yes, we should do that as a capital.
That was going to be my follow-up question was like, should all reserved words, is it best practice for all reserved words to be capitalized?
It is, but it's also very common to see a SQL statement that's written all in lowercase. But it is somewhat of a best practice, yes, to do them on upper. Okay, go ahead and do the challenge. We've only got one more to go in this unit, I think. Yep, one more video and challenge to go after this, and then we will wrap up with the fun stuff, which is updating and deleting data from the database. All right, this one's a quick one, so let's just knock this one out. We are trying to figure out what movie is the sequel to this movie, but we only have one table to work with, so we got to join that data together. So the way that we do that is we say select the movie's title, and we're going to do that. And oftentimes when we build a query, we don't build it in the order top down, right? Just like when we're coding, oftentimes the order that we write the code is not the order that it ends up being. So we can think about this as breaking this up. And so we said, all right, select the movie's title from the movies. And then what we need to do is join back in the movie's title, excuse me, the movie's table, so that we can figure out what the sequel is to the movie that we are selecting out here. So we are going to say left outer join the movies table again, but basically alias that as the sequel table. We are then going to tell it on the movies ID is equal to the sequel, again using our alias here, dot ID. Now, it doesn't look like any of that has worked, but because we have overlapped the movies table, named it sequel, and told it how to overlap those two, we are able to come back in here and say also go to the sequel table and grab out the title. And then finally, it does say that I think it wants it as sequel title. And sorry, this should be the sequel ID that we're overlapping it on. So now we're able to say, hey, Philosopher's Stone is the first movie, Chamber of Secrets the second, Chamber of Secrets, Prisoner of Azkaban came after that. And if we go all the way down, we get to Deathly Hallows Part 2. That was the last movie, so there is no sequel. So we get to null here. Any questions on that?
Oh, I did it a bit differently. Like I like renamed like move like the first movie as like M1 dot title as movie titles and then M2 dot title as like sequel title. And then did like the exact same thing that you just did.
That will get the job done as well. Yep. Cool. Let's go to the last section, the last video in this section, and then we will wrap it up. Believe it or not, this is the hard stuff in SQL. The next section is a little bit easier with updating information, and then we will probably get out of here a little early. So let's finish this one up.
Now I want to show you a combination of joins and self-joins. So this time I'm back with multiple tables, tracking the students and their projects. Now, since I have students working on great projects, I want them to review each other's work in pairs. For example, hyena habitats should review carpet physics. That's why I've created this new table, project pairs, and all it stores is two project IDs that are paired with each other. Now, let's see. What do I see if I select star from project pairs? Ugh, okay, it's just a bunch of numbers, a bunch of IDs, all the IDs that are mapped with each other. It is not the most human readable output at all. What I'd like instead is rows of project titles paired with each other. The project titles are in the student projects table. So that gives me a clue that I need to somehow join project pairs with student projects. Let's see what happens if I do that. Aha! So now we see project IDs and project titles in each row. What I eventually want in the results table is to see two project titles in each row, not just one. So that's another clue that we need to do another join, a self-join of student projects with itself, so that we can get those same column values twice. Now, it may not be obvious how to add a self join at this point because we already have a join. If we want to add another one, we can actually use the join keyword again. So join student projects, and we need to make sure we give them different aliases so that they're not ambiguous. So A and B. All right, so now we've got a lot of stuff in this results table, but if you'll scroll, you'll see that the project titles show up twice in each row. So maybe let's make it easier to see. A.title, B.title. Great. But we still have way too many rows because we're matching every row with every other row, and we haven't added the on clause, the very important on clause. So we're actually going to add 2 on clauses, one for each of the joins. So on project pairs dot project 1 ID equals a.id, and then on project pairs dot project 2 ID equals b.id. Aha, there we go. So thanks to this combination of joins and self-joins, we can see a nice list of project titles paired with their project title. Now, you can use as many joins in your query as you need to get the data that you want, but generally, more joins mean slower queries. If you're interested in how to figure out if your queries are slow and making them more efficient, we'll talk about that soon. So stay tuned, keep at it.
Okay, on to the challenge. One more minute and we'll go through this. All right, let's give it a try. First step, use the join table to display a table's showing the people's names with their hobbies. Okay, well their name is in persons. Hobbies has a person ID. This person ID is going to relate to the ID over here. So we're going to say select the person's full name and also select the hobby's name from the person's table. And we need to join in the hobbies table on the person's ID lining up with the hobbies dot person ID. So this is a good reminder of however we do our join doesn't actually have to be part of whatever we're selecting out. And the resulting table gives us the person's name and the hobby's name. And of course, we could always alias this, right? And say something like as hobby name, and that would also get the job done. Okay. Next step. Use a Austin, I'll come to you right after this, and then Terry after that. Use a select with a join to show the names of each pair of friends based off of the data in the friends table. So why do we need to do that? Well, if we take a look at the friends table, it just says person ID, person 1 ID and person 2 ID. Obviously, that's not very helpful. This is what we call a intermediate table or an association table. It's a way that we solve what we call a many-to-many relationship that we will be working on tomorrow, which is basically how do we store data properly in the database that has many people can have many friends. So how do we properly store that data? This is how we do it with that association table. So in order to make that association table a little bit easier to work with, what we do is we say select, and now we've got a problem. We've got full name, but do we mean the full name from the first friends table or the full name from the second table? So what we're going to do is we're going to say from friends, and we're going to join in persons, right? Because we need the information up from the persons table, and we're going to call that persons A. Then we are going to say on a persons A dot ID is equal to the friends table person 1 ID. Then we are able to select person A dot full name. Persons, and we are now able to get the full name from that table. What do I mean by that? If I add this select back in to the friends table, I'm able to see person 1 ID is 1, person 1 ID for the second row is 2. Person 1 lines up with one ID is Bobby, ID 2 is Lucy. So that's what we're getting down here. We're getting Bobby and Lucy, which is representing the left part of our friends table here. So we're basically getting Bobby and Lucy and building them in, linking that data. Now we do that again. We're going to do another join persons as persons B. And we're going to say, hey, link persons B dot ID up to the friends table again, but now they're going to be person 2 ID. And we need that on person's B full name. And if we comment out our other select, we are now able to get the data that we actually care about. And we could even name this as friend 1. And as friend 2. Or friend A and friend B may be more. Okay. Terry, you had a question? Did you figure it out?
No, like I'm just like trying to understand on like I don't know, maybe I'm like overthinking it, but it's on just pretty much just combining like just two tables into one and you gotta like specify like each like row or
Yeah, so I think it's really helpful to do this in a spreadsheet. So let's say that we've got our persons table, right? And that has an ID and their name, right? So let's just say ID 1, 2, 3. Then we also have our friends table, and that has an ID, has a person A ID and a person B ID. And we're going to say 1, 2, 3, and then I will say, I am friends with Terry. I am friends with Austin, and Austin is friends with Terry. Well, how do we know that? Well, when you're looking at this, you're like, well, person 1 lines up with person 1 over here. So I know that person A is Max. Well, how do we tell the database to do that? We say, hey, go to the friends table, go to person A ID, and on that information, line it up with the ID from the persons table. So what we're basically doing with that on is we're saying link this one here, which is the person A ID in the friends table, to the one over here, which is the ID from the persons table. So we're linking these two together. Then in that example query we just did, that wasn't enough because I not only wanted to get Max, I wanted to know whoever person 2 was. So the on linked friends again. This time it took the person B ID and linked it back over to the persons table ID to get Terry out and linked these two together. What do you mean? Does it matter what you make it equal to?
Like if you made the ID from person's table equal to the friend's person A or vice versa.
Like if you flip the order of these two?
Yeah.
Yeah, the order doesn't matter.
Okay.
And Austin, I'm glad you got your question figured out. Okay, any questions about joins? Any questions about anything that we've covered in this module? Any questions about any module we've covered up until this point?
I do. You might have kind of answered it. I just maybe it needs to soak into my brain. But is there a way to get the same result from like selecting from persons and doing it in another roundabout way, or is this the only way you can get this result?
You're saying put persons here?
Yeah.
Yeah, you should be able to make that work. You should be able to say
You would just need more join ons, right? Because you need to join friends
from
Right.
persons, join friends. Theoretically, there is a way to do that. Persons as
Okay, that's where my brain went to first. That's what I was asking. I didn't know if I was thinking about it wrong or if it is possible and I'm just thinking about it inefficiently.
that does the same way. That accomplishes it.
Okay.
And from the chart that you send us with inner and outer, so if you use like left outer, it's just returning all the data from the left table.
Yeah, so that would be if I said join persons, if I said left outer join persons to friends, and I put a friend in here called lonely, I would see that lonely has no friends if I did a left outer join. If I did a inner join, lonely would not come back in my results at all because he's not in the friends table. So if I did an inner join on my friends table, I would get back 1, 2, 3, person A, person B. Let me blow this up too so you guys can see it a little easier. And then you would see Max and Terry, you would see Max and Austin, and you would see Austin and Terry. That's an inner join. The outer join would, but we wouldn't get lonely at all because lonely has no friends. If we did an outer join, and this would be a left outer join, and we put the persons on the left side, we would actually get back over here lonely and null.
Okay, that makes sense to me now. Because lonely don't have friends on that table.
Correct.
Gotcha.
So the inner join is taking just the intersection of the Venn diagram. If the left table is the left, I'm sorry, if the person's table is the left circle, the friends table is the right circle. In an inner join is only taking the intersection of those two compared to the left outer join, which is taking that intersection and using it to fill in all of this information. But then it's also going to take anything over here that is not included here and just show it as null.
Quick question.
Yeah.
You don't have the ID set for left outer join. Is that intentional or is it supposed to be pulling from the actual ID of the person's table ID?
You're saying in this example or in my code?
No, right here, the left outer join. You have 1 for Max, 2 for
this, it depends what you're representing. If you're representing the person's ID, this would come back as, well, you would have to specify what ID you wanted. If you wanted the person A ID or the person B ID.
Gotcha. Okay.
So it depends what you added in your select. But if you just said persons.id, it would come back with an error that person's ID is ambiguous because it's like, well, do you want this ID? Do you want this ID? Or do you want these IDs?
Right.
And so you would have to be specific there. So really in the results, this would probably be the better way to do it. Unless you, for whatever reason, specifically said, oh, give me person's A ID. And then at that point, that information would show up and this would be null.
Gotcha.
And full just takes the entire data from both persons, table, and friends.
Correct.
Okay.
Yeah, so you could say, yeah, full, you very rarely use a full because at that point, you're not really overlapping any of the data. So I don't think I've ever seen a fool used in reality, because normally you want to know, hey, I need all the table from the left, or I need all the data from the left, or I need all the data from the right. And if there's not any overlap, that's fine. But you get a lot of weird results on way more rows than you expect when you do a full. Okay. Go on break. If you've not done attendance, the secret word is relational. If you already did it, do not do it again, please. Go on break. Be back at 7:25. We will finish up with updating and deleting rows and modifying table structures, and we will be done with intro to SQL and get on to database design tomorrow. All right, so what have we seen so far? Well, we've seen selecting data from a table, right? That's reading operations. We've seen inserting data into the table. That's creating data, CR. What we haven't done anything with, though, is updating any of the data or deleting any of the data. And so that's what we're going to finish out tonight's lesson with. So the article that they come up with is saying, hey, we've been doing some read-only operations or read-write operations. And so a read-only operation is obviously going to be the safest thing that you can do in a database, because you can run the query a gazillion times and the data is never going to change. However, there are times that we do a read-write, for example, when we do an insert. But sometimes we also need to be able to modify that data, right? Say, oops, I made a mistake. I need to update that row, or, oh, I want to delete the row altogether. So we want to be more careful whenever we are doing a write operation, whether it's an insert, update, or delete, because once we run those commands, there's no way to get that data back. There is no Command Z in SQL. And so what we have been seeing so far is all of the commands have been listed out, right? And we are seeing the live output of that. That's just how Khan Academy has it set up, though. When we actually are working with the database, we are going to hit the execute button. And when we hit execute, that query is going to be run. And there is no, oops, undo that last query. So we want to be really careful when we're working with that. In Khan Academy, it's easy enough to just delete out that query and all of a sudden our data reappears, right? That won't be the case in actual databases. So we want to be careful with that. And the good news is for our capstone, we'll be working with a lot of dummy data to get it going and get it up and running. But once we do have that data in there, we want to be careful about things like database backups and things like that, that Nathan will cover down the road. So anyway, let's dive into our update and delete operations.
Let's say that we want to create tables to store the data for a diary app. A basic setup would be a users table and a diary logs table. Now, when a user wrote up their diary on the website, we would have some code to execute an insert statement like what I'm pasting in here. So this inserts 2 rows for 2 diary logs, one day after the other. First, where somebody has a horrible fight and buries their rows in 3 pounds of dark chocolate, and the next day, of course, they make up and celebrate with ice cream, as you do. So we can check to see what our diary logs table looks like now, and we can see those 2 posts in there. Now imagine that the user comes back and wants to modify their logs, maybe because they don't want to admit, even to themselves, that they have eaten that much dark chocolate. Now, we've already inserted the data, so at this point, we would need to have code that would execute an update statement like this. Update diary logs set content equals I had a horrible fight with Ono's guy. Now, this is telling it to update that table and set the content, but it's not telling which row to update. We need to tell the database which row to update because we don't want it updating every row with that content, just one row. So how do we find the log to update? Well, we can use the ID like that. If we didn't know the ID, we could also filter by columns that we knew were unique to the log, like user ID and the date. It was 2015 0401. But really, if you know the ID, it's safer because you're not relying on having to filter on columns, which could actually be the same across multiple rows. If you might have a diary app where users are allowed to write multiple logs per day. It really depends on how the app and the tables are designed. I'll go back to the ID since I know the ID. Now we can do another select to see that our table changed. And it did. No more knowledge of those 3 pounds of chocolate. Okay, so the user made that change, but then the user decides that they actually want to delete the entire log entry. Like maybe because they want to forget that they even had that horrible fight. So in that case, we would need to have code to execute a delete. So we can say delete from diary logs where, and once again, I'm going to use the ID because I know it. And let's select again to see what it looks like. Haha! So we only have one row left, which means that our delete worked. Now, you should be very careful whenever you're doing update or delete because you want to make sure you're updating the actual rows that you intend to update. You don't want to update the wrong rows or delete the wrong rows and lose that data. In fact, some apps never issues deletes. They never really delete rows. Instead, they add a deleted column to their database, and then they'll do something like deleted equals set deleted to true when the user wants to delete, and then they filter based on deleted equals false in the select queries, something like that. So that means that you never actually delete data, which can be a little bit safer, but it's a little more complicated to do that as well. So anyway, that's up to how you design the app. So now with select and insert and update and delete, you have all the commands you need to handle what a user would want out of your diary app. And now hopefully you can better imagine which commands are happening behind the scenes when you use your favorite apps every day.
Okay, on to the challenge. Go ahead and have Code Academy. No, oh, there we go. Go ahead and get some practice with your update command. And then go ahead and do a select after the update to make sure that the update actually processed the way that you expect it to. And then right after this, you'll do a delete. Only going to give you guys 2 minutes on this one because it's a pretty quick one to write out, but we'll give you some practice. Only one more video to go after this one, and believe it or not, I know I say it all the time, but I think you guys might actually get out of class a little early tonight. All right, let's go ahead and go through these. So the first request is to update the table called documents, and we need to correct where the author, so we're going to say set author equal to the new value. And it would be really bad right now if I just threw a semicolon in here. Look what happens if I do that. If I throw that semicolon in and then say select star from documents again, I'm going to see that all of my authors are now Jackie Paper. So even Puff TM Dragon has now been overwritten, and all of them are Jackie Draper. So you want to be careful. You don't want to just do the set here. You do want to say where the author is currently equal to Jackie Paper, and that will make sure that Puff TM Dragon stays in and we don't overwrite everyone. So without putting that where clause in, and we've seen that where clause before, right? We saw that in our select to filter the results. We do the same thing in our update. We say, hey, only update the author to Jackie Draper where the author was Jackie Paper before. So step 2 here is now delete a row. Be careful not to delete all the rows. Only delete the row where the title is things I'm afraid of. Then reselect all the rules to make sure that the table changed the way you expected. So we are going to delete from the table documents where the title is equal to things I'm afraid of. And then we will select out the table again. And we are able to see that the things I'm afraid of, which was row 5, is now missing from the table because we deleted it. Hopefully pretty easy. Commands that we will be running very frequently, though. Any questions? It's like you guys are still typing, so give you guys a minute before we move on to the last video and challenge.
I have the same thing, but it's not.
Be careful, it needs a select from documents, an update, a select, a delete, and then another select. And semicolons at the end of everything. And if you still don't know, let me know and you can share your screen.
Yeah, I'm gonna share my screen real quick.
Go for it.
The clip should be oh, I updated my computer, so not switched all my different desktops around. I think this is right.
Yep. Select. Custom remote. Capital A on afraid. Anyone else need help? Or have questions?
So we need to specify like where we want to delete, otherwise it'll just like delete everything. Oh wow, that's crazy.
Yeah, and that is a major oversight that the founders of SQL were kind of like, oops, I guess we should have been a little bit better with that. So newer databases will have a setting where they will basically say, we won't let you delete everything in a table unless you explicitly like hit the OK button or like, yes, I mean to do this. So some databases will have a configuration that will kind of prevent you from doing that accidentally. But oftentimes what you'll end up doing is before you write a delete statement, you'll change the delete from to basically a select star from and make sure that your where is filtering just the rows that you mean to either update or delete. And then you can change that select star from to the delete from and actually execute it. But oftentimes it makes sense to do like a little preview of what will update before you actually issue the update.
Oh, so that also apply with update too. Like, does it like give like a confirm where like, oh, are you sure you want to like update all your like your records and stuff? So like so
Um, yeah, yeah, it will. But again, that depends on how the database is configured, and some of them aren't enabled by default to do that. So you do want to be careful with your queries. We'll be working with dummy data right now, so it's not like you're going to really break anything. And we're going to learn about a safer way to interact with our SQL code in JavaScript using something called an object relational mapper. And that's going to allow us to write our queries in JavaScript and will force us to say, hey, if we want to update multiple rows, we'll actually have to set something multi-true. Otherwise, it won't let you delete multiple rows or update multiple rows unless you intentionally say, that's what I am trying to do. So we won't be interacting with SQL a ton directly. However, it is still important to teach you that because what the object relational mapper is doing under the hood is using SQL to interact with the database. It just so happens that it's mapping it into an object that we can use in JavaScript. Um, so it is, we won't dive into that until next week. But tomorrow we'll go over database design and set up our to-do list app. And then we'll work with SQL directly. We'll make our first API. And then on Thursday, we'll dive into possibly the ORM, depending on how long everything takes tomorrow. Okay. Any other questions before we finish up this lesson?
I had a question in the chat.
Oh, sorry. Beekeeper Studio, if you write the SQL query directly, it won't do it. But if you're editing the data in the UI, it makes it much harder to like accidentally delete all of them because you would have to hit like Command A and then hit delete and then hit confirm to actually execute the query. So Beekeeper Studio will force you to confirm everything before it actually executes it. But if you're writing the raw SQL out, it will let you do a mass delete or a mass update. Yeah. And Beekeeper Studio is what we'll be using for everyone else is the user interface that we'll be using with our Postgres databases locally. So we'll learn how to get all that set up tomorrow and Thursday. Okay. Oh, one final note before we go into the last lesson. I posted a article about database design. We will be covering all of that content tomorrow. I've got my own slides for it. But if you're someone who likes to pre-read and kind of have a leg up and you know, read about the content before we cover it, it may be a good idea to read that article before tomorrow. Otherwise, it's a good recap of everything that we'll be talking about in database design. It is a couple page read. It will probably take you 15, 20 minutes to read it. But it is totally fine to reread that over the weekend before you do your database design. Or to wait until you see kind of what concepts you get from tomorrow's class and then decide what sections you want to reread from there. So that is updated in the Canvas assignment. And I also posted it in Slack. So if you are one of those people who like to pre-read, that article is there for you. Okay, let's dive into the last section.
We're back with the database for our diary app. Now, when we first created these tables, like the diary logs table, we decided to store user ID, date, and content. And now I want you to imagine that a few months after we launched this diary app, a user designer suggests adding a "How are you feeling?" drop down on each diary entry. And the user would say something like happy or sad or confused. In order to store that, we need to add an emotion column to the table. Now, we could just add it like this, but if this was a database for an app in a real production environment, then we couldn't just edit the create statement because that's something that we actually issued months ago and it's already happened. And if we rerun it, it'll actually remove the current data. And we don't want to lose all the data that we've gotten over these many months. So at this point, after we've done create and after we've got data, we're going to need to use the alter table statement. And to use that, we write alter table and then the name of the table, and then add, then the name of the column name we're adding, and then the data type of that new column. Great. So now the next time that the user makes an entry, we'll need to specify that column, or we can specify that column. So let's say, all right, let's say they went to Disneyland, and to specify that new column, we're going to put comma emotion, and then here we'll just say happy. Most people are happy that go there. Okay, so let's see what it looks like now if we select it all. So we can see the latest row has happy in the emotion column, and the row before it has that big old null in it. And that is what databases usually do. They fill in null for unspecified values. If we want, we can actually get it to fill in some other value for rows where it wasn't set, and that's what we think of as the default value for a column. So to do that, if we had wanted to do that, we would have put default and then the value in that alter table statement when we ran it. So now you can see instead of null, we see unknown. So that's an option for you when you're adding a column, and just something to keep in mind, depends what you're adding to the database. Okay, so now let me show you something that you rarely do, deleting an entire table. Maybe I would do this if I migrated all the data out of this table into some new table, or if I just got mad and decided to be a horrible person and take a rampage all over our database. That's bad. But anyway, we can do this using the drop table statement. And now if I try to select, what happens? I actually get an error because my table no longer exists, so it can't select from it. So that was a bad idea, and I'll just delete it. You should think really carefully about dropping tables. Do not just drop them willy-nilly. You should also be careful with alter table, especially if you're running it on a table with a lot of rows, because you can have performance issues there. Really, I don't want to scare you, but you should be careful whenever you're making any changes to your database. With great power comes great responsibility. And now you have both.
All right, let's finish this up. I will do a really quick summary of the last article, and we'll try and get you guys out of here by 8 o'clock. Just give you guys a couple minutes to work on the alter table command here. Going to insert some data after that. And then I think we drop the table maybe at the end. Can't remember what the last challenge is. So go ahead and work on this. Give you guys a couple minutes, and then we'll go over it. Well, way to ruin the fun, Austin.
You really meant it when you said we already did the hard part.
And out of all of the joins, all the ones you'll ever really use is an inner join, unless you go into a workplace where they're like, hey, we've got 1,000,000 rows in the database and we need you to run these queries for us. Please write them. But in the context of a full stack web developer, if you are interacting with the database solely through your code, chances are the relational join stuff you won't have to worry too much about. You'll definitely use relational data, and the ORM that we're using has the notion of relations, but basically we will set up in what is called a model. We'll define the relation and then say include the data, and it will basically do all of the hard work of the join for you. So again, it's important that we cover this because you do need to understand what SQL is doing under the hood. And depending on what kind of company you're going into, you could definitely need to write raw SQL to execute those commands. But what we'll be learning in the next 3-ish days, and then reinforcing throughout the entire full stack module, is how to use an object relational mapper to do all of the SQL heavy lifting for us. But that won't be until Thursday or Monday.
I do have a question, but we can wait until after we go through this.
Sure. Anyone need another minute before we go through the answers? Okay. Get through this as quickly as possible. Use an alter command to add a price to the column. So we are going to say, I'm typing alter table clothes. We are going to add a column called price, which will be a type of integer. And then we'll do a select star from clothes to make sure that the table got added. It indeed did with the price. So we are going to then update the information. So update clothes, set price equal to 10, where the ID equals 1. And then we got to rinse and repeat. 2, 3, 20, 30, select star from clothes. Or did I make that all uppercase? That got our prices in. And then finally, they want us to insert a new item, including price, to one final select. So that's going to be our insert into clothes. I don't know, in honor of the Olympics, let's add a Speedo that's red, white, and blue. And then the last thing we need to do is add a price, and nothing sports equipment is cheap, so it will be $1 million. And if we select that out, we are able to see my very expensive Speedo has been added to the table. Any questions on that? Okay, so the last article I am going to summarize very quickly. These are kind of all SQL concepts that you should be aware of when working with a database in general. One was one that we already talked about, avoiding bad updates or deletes. Basically saying, hey, before you run an update, try and do it as a select and make sure you're not overly or accidentally updating more info than you meant to. There's something called a transaction, which is basically saying run these two commands And if either one of those two commands fails for some reason or gives an error, it will roll back or not apply anything that was applied in that transaction. So let's say it did this, it had no problems. Then it went to do this and it was like, oh, user ID 2 doesn't even exist. What it will do is it will back out that first command that ran and say, hey, because the second one ran with errors, the first one, we're not going to apply it. So transactions can be really powerful. Making backups, very, very important. Obviously, if you have some production data, our backups at Tuzag run every night at 3 a.m. So it's basically exporting out the entire database, so that if someone deletes something accidentally, I can go back into the database, backups, find that information, and reinsert it. They did mention what if someone gets like really angry and goes in and just starts dropping tables. Believe it or not, that happens more frequently than you would imagine, especially if a disgruntled employee gets fired. And so you want to be really careful because some people get vindictive and they go in and they have database access because they need to do their job. It's a legitimate thing people need. And they just go in and they delete your entire database. And all of a sudden, not only does your entire app crash because it can't find any of the tables, but you could have years of data in that database, right? My boss and I have been building, and he's been working with the software I built for 8 years now. He has spent at least 40 hours a week, at least 48 weeks a year for the past 8 years loading data into that software. Imagine all of a sudden if the software just lost everything that was in the database. I would be fired very, very quickly. And so we have database updates that run or backups that run every night at 3 a.m. We keep those backups for 2 weeks or 30 days. I can't remember. But then we have set up that you actually can't delete any backups if they were created in the last 14 days. So if I wanted to, even as CTO, even as the one who set up the backup system, even as the Google Cloud admin, as the person who set all of this up, there's actually a security policy that doesn't let anyone, including myself, delete a backup if it was created in the last 14 days. And so that's just a safety mechanism to basically say, hey, the disgruntled employee could also have access to the backup system as well. And so Google has created a way to basically lock that out and say any newer backups can't actually be deleted until that time elapses. Replication, slightly different concept, but along the lines of backups. It's basically to say, hey, if your one database server goes down, it will replicate over to a fallback server and it will keep those two in sync. So that's something that SQL and Mongo do very well. And now with the cloud, it's possible to set up replication across multiple different zones or regions. So basically saying, hey, if California gets hit with an earthquake and knocks that entire data center offline, it will go back over to a data center that's somewhere on the East Coast and pull the data from there. So replication, we won't be doing that on our databases and it gets expensive to replicate data, but that is a very useful thing if one goes down, falling over to the other. It's possible to grant privileges. So if someone only needs read only access to the database or only needs to be working with certain tables, it is possible to basically limit the access down to that based off of how they're signing in. And those are all just basic concepts to know. Any questions on that? Or where we're headed or anything from this evening?
Yeah, I got a question real quick.
Yep.
As we're I come across it quite a bit where at work, since the population isn't as tech savvy and they've only been accustomed to spreadsheets and they want to do everything in a spreadsheet.
Yep.
Where is the line that I can be like, because I'm not like a data scientist, but you know, a concrete line that like, hey, if it meets this criteria, it should become, you should reach out to like an applications team or something.
Yeah, really good question. And Microsoft has kind of blurred this line with Access, which is
Yep.
a very old product that is not used a ton anymore, but refuses to die because it was that general idea of what if you need more than a spreadsheet, but you still want a user interface that people can use to update the data and interact with it. So apologies in advance, Joe, if you go into that article and are triggered by some of the Microsoft screenshots in there, because that article was, while the principles hold true to all database design, the article was written for people who are like, I'm in Access. How do I know how to design a database and like follow all the right rules, basically? So what's the line? When do you need to get out of a spreadsheet and get into a more fully featured database? Basically when you cross the thousands of lines row, when you're dealing with, let's say, over 10,000 rows in a spreadsheet, the spreadsheet is going to start to bog down. Whenever you need to get into user permissions, that is something else that a spreadsheet does not do particularly well, that a custom application will, right? Oh, only admins are able to create new rows, but certain users will be able to view this type if this dropdown is set to this thing, right? That's a good example of what you can control with application logic in a database that you wouldn't be able to normally. If you're getting into data analytics of, again, tens of thousands or hundreds of thousands of rows, Excel or Google Sheets or whatever is just going to crap itself compared to SQL, which will scale up to that. So we did a project at work for a health insurance company in the Midwest. And they were like, we can't give you this data. Oh, and you guys are welcome to head out if you guys are, if this isn't interesting to you, you're welcome to head out, and I'll see you guys tomorrow. Um, they were like, no, we just can't give you this data. And we were like, oh, we've already signed all the security policies and, all of that. Like we were licensed contractor, we had HIPAA, all of that, right? And they were like, no, we just can't give you the data because it's 9 million rows in our database. And we were like, and they were like, it will crash Excel if you try and open it in there. And we're like, of course we're not going to open 9 million rows in Excel. Like, are you insane? We're going to do data analysis on it in SQL. And they were like, oh my God, you guys know how to do that? There are only 2 people here who can execute SQL queries against that large of a data set.
Did they have somebody open it on like Monday morning so it was ready for Friday afternoon?
I just So yeah, when your data gets that, which, an insurance company, they got to track all the claims, they got to track the diagnostic code and the procedure code and all of that stuff. But when we came back and we were like, so what's your most expensive procedure? They were like, oh, we don't know. We were like, well, that would kind of be helpful information, don't you think? They'd be like, yeah, that'd be great if we could actually get that. And then when we were like, okay, well, how much are you paying for, let's say, broken bones? And they were like, oh, we can't get that information because the diagnostic code is broken left arm, broken right arm, broken left leg, broken right leg. We don't know how to query the data to basically group all of those together so that we know broken bones, no matter what broken bone it is costing us this amount of money. And so when I was writing those queries, I couldn't do that in Node because there was literally not enough memory to work with the data set that was that large. SQL looks at that and goes, yeah, that query may take 20 or 30 minutes to run, but because SQL is optimized to work with that large of a data set, it was able to bring back that information when I was able to do a relational table and say, hey, this diagnostic code lines up with broken bones in general. This is what we're trying to group it to. So whenever you need basically a user interface for interacting or updating the data, that's a great time to use a database, get out of a spreadsheet. Whenever you've got a huge data set, whenever you need to control access to the data, whenever you're trying to display the data in some custom chart format, or you want to have more control over it, when you need a user interface that's more mobile friendly, that would allow them to quickly search, by a patient and get their information, as opposed to scrolling down a spreadsheet that obviously isn't going to fit well onto a tiny screen. Anything that's form driven is often a better use of a database.
Yeah,
That's all I can think of off the top of my head.
a lot of the things that they end up doing are like, hey, we want to there's a regulation that overlaps between the lead program and early intervention. So they'll be like, well, we want to cross compare to make sure that we're covering, if lead sees a kid and they're marked as high lead level, they're also automatically going to qualify for early intervention. Do you guys already have them in your program, so we're not doing extra work, or we can, do the based on the regulation who goes first. And trying to do that with like manually, like having everybody have access because it's all in a common drive that is on a server that everybody has access to. There is no user interface to update like the referral log and the lead log and everything, and then trying to query all that data together where you have it's not like I wouldn't even say like active cases are in the tens of thousands, but you still have like a lot of different variables in there.
I was doing contract work at one point, and a company had come to the company I was working for, and they were like, hey, we've built this entire system. We're a major landlord in the Syracuse area. We have 1,000 rental properties, and we run it out of this one Excel sheet. And this Excel sheet had some Visual Basic scripts in it, but not a ton. And it was basically the entire business, from tracking maintenance requests to making sure rent was paid to flagging the leasing progress and status, all the way through to move out. I mean, this was the most advanced Excel spreadsheet I had ever seen. And they had come to us and they were like, we've outgrown this. We need something better. And we were like, wow, well, someone's clearly invested a lot of time into this. Why do you like, we can capture all of these features into an app, a custom app. It's going to cost you 50 grand to do that. But what's your pain point? Like, why do you need to improve off of Excel? And this was, I don't know, 7 years ago. And so they were like, oh, there's really only one reason, because this does everything we need it to. Multiple people can't have this Excel file open at the same time. It gives errors. And then we literally have to like go around the office and ask people to close it so other people can open it. And I'm like, and I went to my boss at the time and I went, they could just use Google Sheets. Like, Google Sheets doesn't have that requirement. And he was
Thank
like,
you.
shut up. He was like, shut up. This is a $50,000 job that we could be building in the custom interface. And of course, that was like the better answer and the long-term answer and all of that. But I was like, but if this is all working for $1,000, we could move this over to Google Sheets and rebuild out the Visual Basic, stuff, and you could just run it from there. So the line is definitely blurred between those two. And then I think another reason is relational data, right? At a certain point, you are duplicating data just to get it to work from multiple tabs. And that can get really messy. And then you run into performance issues as well of like, there are so many rows in this, or we've had to get hacky. Excel and Google Sheets for a long time had a 1,000,000 cell limit. And so you couldn't have more than 1,000,000 cells, whether that was rows or columns, across all of the tabs. Um, Formulas are obviously unmaintainable when they get to be so long. They're wrapping on multiple lines. Excel and Google Sheets now support JavaScript. So you can write custom formulas in JavaScript, which make it a little bit more maintainable, but still not the end of the world, or not like super great. So yeah, there's a lot of answers there. There's no like de facto you've crossed this line, time for a database. But there is certainly a big gap between the user friendliness of a spreadsheet and the SQL nature of database design
Yeah, so
and SQL query writing.
right, yeah. Sometimes I have a hard time articulating that point to people where they're like, we'll just build it in Excel. I'm like, please don't.
It is, and Access was really a godsend to people who didn't want to learn SQL but had a legitimate need for a database. Um, it's a Microsoft product, so I hate it, but there's very little like it that actually bridges that gap.
Starting at this job, working at the county, I have come to despise Microsoft products. I I used to not like Google products because they were only available online, but I'm like, it's totally worth it. I don't care anymore.
Socket-based updates and throwing the entire doc and docx format out the window and saying there's a better way to store all of this data is
Live
exactly
authoring,
why Google has had the success that it has.
live author, macros, everybody updates at the same time. It's great.
Yep. But even everyone updating at the same time can cause issues of like, if you've got 100 people using the application, Google Sheets will scale to that. But if you got 100 people trying to create a new row all at the exact same time, you're going to click in and start typing something, and they're going to be
We
on that row because it's the
we
first
had that
new row.
problem at TCG with the what the hell was it called? It was just updating the inventory log where the discrepancy log. So if you ran into things that like there wasn't any cards that were in the inventory, you would have to go and manually put it in line by line. And this was like this had thousands of entries. For like for every order that comes through TCG. So they had to physically set all the computers that had access to this document right next to each other for that reason.
Yeah. So, lots of reasons to use the database, but lots of downsides as well, right? And we're going to go into database design tomorrow, and then we're going to be running our first SQL queries. And then you'll really get an understanding of the database doesn't connect directly to the front end, right? Because if it did, there would be no access control. There would be no, hey, only admin should be able to do this. There would be no logic layer basically between the database and the front end. And so we put the back end between the database and the front end, which is ultimately going to be our first API that we create. And so you will see, even for a simple to-do app that we'll be creating tomorrow or Thursday, there's like 300 lines of code to just get one to-do list item to show up in a front end. So databases are not, how easy is it to create a new spreadsheet versus how easy is it to create a new database with a proper table structure and all of that stuff. Much harder, but then it also would scale up to the point where if I ship this to-do list app out tomorrow, I could have 1,000 users on it and my database wouldn't flinch. It would have no trouble tracking all of that information.
Yeah, that part seems like it has a lot of opportunity for development and stuff that transition period between, because everybody uses Excel and Sheets and all that are great for small use cases. And then once you translate up, like somebody can make a decent penny making a tool set for that.
Yep.
So would it be better to have like multiple tables doing for having like I guess different like data rather than having like one big table that has like everything like inside of it?
Yeah. So in general, um, more rows are better than more columns, but you do want to break your data out, right? So normally, whenever you have a one-to-many relationship, hey, we have one customer, but that one customer can have many orders. That's where it makes sense to have a customers table and an orders table, right? Because one of the things that we're going to learn about database design tomorrow is we never want to duplicate data, right? And then the same goes, oh, well, this user has an address. So do we put the address on the order or do we put the address on the customer? Well, initially you go, well, you put it on the customer, right? Because then when they order something again, we just reuse that address. Well, what happens if they change their address after placing their first order? Well, now we don't know the address the first order was sent to because they updated their address in the customers table, and now we've lost that data. So at that point, it actually makes sense to add in a third table called addresses that is linked both to the customer and to the order. So there's all kinds of database design, and we're going to do an overview of all of that tomorrow of like how do you make those tables? How do you figure that out? And then the weekend's homework assignment is to create something called an entity relationship diagram or an ERD. And it's basically a diagram of all of the tables that you need for your capstone and how they relate to each other. So we're going to go over the basics of database design. Then we're going to design a database in an ERD so you get an idea of how to do that. And then from there, you'll be able to submit your ERDs and get feedback of them on them for your capstones before you actually build out the tables.
So would it be better to have like a table for the person's username, password, and like the comment that they write on like let's say they like post something on Facebook. So
So
you
two tables for that.
all two tables?
Users with their username and password, and then another table for comments, which is going to store the user ID and the content of the comment.
That makes sense, yeah.
Right? Because otherwise, if you did it all in the users table, you would have to put their username on every single row and their password on every single row. So the best way to think about it is like, how would I build this, sorry, Joe, in a spreadsheet without duplicating any of the data? And every tab that you do is going to be another table in your database. And that's how you can kind of play around with the data. So when I make an ERD, I lay out my tables, I lay out the columns in them, and then I go create dummy tables in a spreadsheet. And then I go, oh, oops, I'm storing username in both the users table and in the login credentials table. I need to either merge those two tables together or I need to be careful about where I'm storing the information. But again, we'll ease you into that with the rules of database design, and then you'll have the weekend to practice with that for your capstone and send in the diagram and get feedback on the diagram before you lock yourself into actually creating all of that. And it's really tough because we covered SQL in 2 days. We're going to cover database design in 1 day. And I took 2 semesters of this in college to learn all of these concepts, right? So there's a good, I don't know, 75% of what I learned in college on databases that I've never used in 10 years. But we could easily spend 3 weeks on all of this to get those concepts covered. So I don't want you to think like, oh, I was bad at creating my ERD. We're just going to blast you with the fire hose of all the database design. You're going to take a stab at it, and then I'll give you feedback of how to tweak it. All right. You guys have an awesome evening. I will see you tomorrow.